Thank you so much. I'm the last talk for the day, so
So better be funny.
I'm going to try. I'm going to try to be a little funny and relaxed, and so you can not fall asleep, hopefully. I'm going to talk about a slightly different direction. Actually, Jim set me up really well. A lot of what I'm going to show you are actual hardware that we're doing as part of the decadal plan that Jim participated in. I'm actually leading a new SRC Jump 2 center that's dedicated to communication, especially both wireless and photonic communication. So hopefully we'll all come together, and I'll show you how photonic connectivity, in particular silicon photonic interconnects, are really poised to revolutionize computing, I believe. So I know you have my bio, so I'm just going to but it's not in there. I just wanted to point out that I've been very involved in OSCAR for many years and in the exascale project. I was one of the authors of that 2008 paper, report, I should say, and was really touting the photonics back then. And as I mentioned, I'm really excited about this Jump 2 Center. It basically includes, Columbia is the lead university, includes 12 other PIs from other universities, and 15 industry partners, including Samsung, Intel, AMD, Qualcomm, and IBM, and others, as well as DARPA. So this is a real all-hands-on center. There are 7 of them across the US, and this is one that's focused on connectivity. Broadly defined. So this is my first time in New Zealand, so thank you for the invitation. I just wanted to, this is a public apology to the country of New Zealand. I violated the biosecurity. So I'm deeply embarrassed. My only excuse was that I was just a little jaded after a long flight from New York. This was the culprit, and it cost me $400, about 40 bucks a slice. So I apologize, New Zealand. I hope you let me come back. Yeah, I had everything. I had the last minute visa, everything. All right, so we all are well aware of the just beyond exponential growth, really just beyond, I think, really understanding growth of AI applications. So, we just like to plot this out, and I have to actually update this chart almost every time I give a talk because it just changes almost on a monthly basis. But if you go back about 6 years, it's about 6 orders of magnitude. Increase in, this is just measuring kind of the model size, right? And so, do you know of anything that's increased this fast in our lifetime? I actually don't. I can't think of anything that's been growing this fast. 6 orders of magnitude in 6 years. And we're getting to the 10 trillion parameter size. Clearly, this exceeds any memory capacity that you can put on a single socket or compute unit. And so this is going to kind of set up my talk, which is really about communications and about photonic, specifically about photonic interconnects. So we have this huge bottleneck. What you see here are essentially we're pretty good on the GPU bandwidth and even on the onboard high bandwidth memory bandwidth that we can get, the HBM. So if we take a socket with the typical, several GPUs, and HBMs all around it, you look inside, you got terabytes of bandwidth. But as soon as you get off that socket, right, you get out of the server or whatever is your entity, it's just shameful how far the bandwidth drops. We're talking going from like terabytes to maybe hundreds of gigabits. Somebody will get really excited when they have an 800 gigabit connection. And that's the state of the art. And so this is a huge bottleneck. in scaling systems, and it also really feeds into this whole energy consumption as well. And so what do systems do? I mean, we talk a lot about HPC, but really the vast majority of systems are data centers built by Google and Meta and so forth. And that's really where, we talk about 20 megawatts, but I don't know, it's a secret, but I bet you they have a lot more power, okay? I know we have the Meta people here, and they're all secretive, but I bet you they're spending a lot more power than 20 megawatts. So we should be very proud of that. That's fine. So this is where the energy really is going. And it's if you look at kind of another way to look at it is the training energy that we spend, right? This is how much power to turn on the machine, and again, even the training energy, and you look at the number of parameters, right? And this is the same sort of growth that we've had in the last, few years, 5, 6 years. And the energy consumption that it takes to do that large model training, large number of parameter training. There was a paper that came out just a few years ago that I really liked because it kind of puts the energy consumption in context of carbon footprint, if you will. And so you have sort of the carbon footprint equivalent of, flying across the US from New York to San Francisco, the human life of 1 year, the car with fuel over a lifetime, and then training one big ass, I should say, training one relatively big, not even that big. This is like 3-4 years ago, big deep learning model, right? So it's a high number. Of course, the US life, it takes a little bit more energy than the average world life. All right. So where am I going? So I'd like to talk about what we can bring to the table with photonics. And this is a little bit of a complicated chart, so I'm just going to walk through it a little bit slowly. It was developed by the program manager at DARPA, Dr. Gordon Keeler, who is running a program called PIPES, basically photonics in the package, something, but PIPES is the acronym. And basically what this chart shows really, really nicely is on the y-axis, on the vertical axis, it's a combined metric. So the higher you are on the y-axis, the better. What it does is it combines bandwidth density, how much bandwidth do I have coming out of my chip, and the energy efficiency in terms of picojoules per bit or femtojoules per bit. Right, so if I'm up at 1 million, that means I have extremely high bandwidth density and also very low energy consumption for moving that data. So that makes sense. And then on the horizontal axis is the distance that I'm moving that data. So if I'm really on the chip right here, you see those like red squares. Those are like the most advanced R&D electronic interconnects that we have, right there. On the chip, very, very short distances. And the electronics is fantastic on the chip. It really is. I can build multiple layers. I can have very high density interconnects. And I'm spending femtojoules per bit on the order of. And that's why, within the chip, I'm really good. And I want to stay in the electronic domain. As soon as I start to move any kind of appreciable distance across the chip, millimeters, but really more substantially, there's almost like a cliff as I get off that socket, right? As I go to DRAM, external, if I go to external memory or I get off the socket, it's really a disaster. And then what happens is we move into these yellow triangles. By the way, the blue dots are just the commercial electronics. The red squares are the advanced R&D electronics, so they're a little bit better. The yellow triangles are basically today's optics, the pluggable optics that you're used to seeing in your data center, and the Ethernet, the 800 gigabit that I showed you before, which is the best that you can get. So those are really good. You can see they can carry us over the long distance, right? We all know fiber optics, you can go kilometers, it's fine. But they're not designed for energy efficiency. And they're not designed for bandwidth density. So they're real low on our y-axis, right? That's where you got that pluggable photonics. So this is, what I'm going to talk about is a new world of photonics. It's a new generation of photonics. It's different. It's up here. It's basically, we have a new generation of silicon photonics, where it's not like the laser and the little lens and the indium phosphide modulator. This is all integrated on the chip. And it's co-integrated with electronics so that we can reduce the parasitics, we can reduce the energy that is going across the electronic photonic interface. And I'll show you some real results. This is unpublished results, fresh off the press. I'm going to show you some record results. So you're really going to be glad you came all the way to New Zealand for this, hopefully. All right, so what this enables us to do is actually get both, the best of both worlds. Extremely high bandwidth density and extremely low, at the same time, extremely low energy per bit. There's no magic, right? We basically get the energy per bit really comes from an electronic photonic interface. I need to drive the photonic devices. I need to modulate the light. And then I need to receive the light. I have a detector, and I convert it back to the electronic domain. That's where I spend the energy, and then there's the laser, too, and I'll show you that. Basically, everything in between is just because the optical, it's very simple. The optical waveguide, the optical medium is just very low loss. And we know this, right? We know this from fiber optics. We can send fiber optics around the world. Those of you that are old enough remember the Sprint commercial pin drop. So it's here. It's technology that's here. That's really what it is. Now, the bandwidth density comes from the great thing about optics, which is that I can send a lot of signals in the same medium, in the same waveguide without interference. I can send lots and lots of wavelengths together. I can't do that in the electronic domain because I'm going to have interference in my signals, right? Just basic difference between bosons and fermions, if you will. But I don't want to go that deep. It's just very simple. So why didn't we do this before? The reason we didn't do this before is we didn't have the infrastructure, right? But we now do. So early in the 2000s, there was a great amount of innovations, a lot of drive in the US, which obviously I'm most familiar with from DARPA, to really drive photonics to an integrated form. We're really going to bring photonics, to where CMOS is. It's not where CMOS is today. I don't want to give any illusions, but we are fabricating photonics, and this is all around the world, in Europe, in Asia, and in the US, on basically 300 millimeter CMOS foundry. And this is a picture of one. I work with AIM Photonics. I work with Global Foundries, Intel. I work with Intel. IMEC in Europe and many other places around the world. So this is now, we can fabricate 300 millimeter wafers that are basically in the same fab as you have CMOS. And we make photonic devices on a mass fabrication scale. So this is kind of what the picture, the basic link looks like. And I should say it's a little bit more our design. There are other designs for it, but this is, I would say our design is the best, of course. So our design basically starts with, so the key to getting bandwidth density is use the one advantage you have in optics, which is you can send data on multiple wavelengths, right? I have a blue wavelength, and I can encode 10 gigabit per second on that, and I can encode another 10 gigabit per second on the next wavelength and the next wavelength, right? Obviously, we're not doing it in the visible. This is in the near infrared, the communication wavelengths. So the enabling device for that is something that's called a comb laser. So this is a single laser that can generate 100 different wavelengths, all at the same time. One laser, 100 different wavelengths, and they're equally spaced, and they're very, very precise. And the reason they were developed was actually for clocking and for metrology. There are places in NIST in Colorado where there are Nobel Prize, type of work that developed these kind of comb technology, right? But now this is on a chip. This is on a silicon nitride chip, and it basically generates 100 channels, and I'll show you actually examples of that for real. So this comb goes into a chip, and you see these little circles, and they're basically modulators. So each one of these modulators encodes data on one of the channels. So it like filters out that channel and encodes data. And you can run those modulators at like 10 gigabit, 20 gigabit. You can run them really faster too, but then there is a trade-off between the faster you run them, because you run them electronically, right? So the faster you run electronics, the more energy you spend. So there's an optimization for, you don't want to go too fast because then the electronics is going to require SerDes and things like that, and that expends energy. On the receiver side, you also don't want to run too fast because then you, in addition to deserializing it, you also need to have potentially signal processing. You can run higher modulation data rates and things like that. So the idea is you want to strip down everything. You want to just go at the tributary rates and just use the parallelism of the photonics, and that's what we did. So this is actually, I'm so proud of this. So maybe I'm just a little bit excited. But this is actually the chip. It was completed, and the results I'll show you are just a few weeks old. They're very recent. So this chip is a world record. It has a bandwidth density of 5.3 terabits per millimeter squared. And it has, and that bandwidth consumes just under 250 femtojoules per bit. So that's where we are. So it's driven by a comb laser that can generate 250. In our example, we have 80 channels that we're using. And each of the channels is modulated at a relatively modest rate. It's a 10 gigabit per second. We can also go up to 16. That's because of the energy optimization. And I guess the rest is a little bit more photonic technical stuff that I'm happy to talk offline. Like things like we developed something called wafer scale undercut, which reduces the thermal power that you need to apply to all of this link as well. So these are just some other details. This is a little bit of the architecture of what it looks like. So we want to use, let's say, 80 channels. But if you put all those rings on one bus, then you start to run into some limitations because there's going to be some losses by the time you get to number 80, right? Just losses through the waveguide and through those modulators. So there's a new design where it's a scalable architecture where we can have a smaller number of channels per bus, maybe 16 or 32, and then scale it up from there. And these little other devices are called interleavers and deinterleavers. So all of those are on that little chip that I showed you. Okay, so now I told you all the really good stuff, right? So there's photonics, and it's low energy, and we can fabricate it in 300 millimeter process, but packaging is a real challenge, okay? So, and the ecosystem for that is really not here, and that's where I was, Jim was kind enough to arrange for me to give some input to the CHIPS Advisory Committee. And all I talked about was packaging, I think. He has the recording. I think that's all I talked about. I didn't go all of that, yeah. I didn't want to make it look too good. All right. Packaging, packaging, packaging. So you can do 2.5D. And that's kind of nice because it's relatively, it's a little bit more straightforward to do. What I mean, you take an interposer and you put photonics and electronics and you connect stuff like that. You can even think like in the future active interposer where you actually, you go all the way through with TSVs and you can connect the photonics and electronics. But this 2.5D doesn't get you the bandwidth densities that you really need. It's a really good thing to do. We're doing it right now. And you can see on the top right side, it's a package that we developed where it's a 2.5D on an interposer. You see the PIC is photonic integrated circuit, the EIC is EIC, electronic integrated circuit, and then an interposer. And then we can then use it in kind of like a system level experiment with FPGAs and things like that. So it's really good for doing experiments at the system level and running different kinds of applications and all of that. But you know, at the end of the day, it's the electronics is here, the photonics is here, you got parasitics, and it's just not, it's also the limitation of monolithic integration, which some approaches use monolithic integration, like in the global foundries process. And at the end of the day, you're still in 2 dimensions. And so you just cannot get that bandwidth density. And you're always going to be limited because you need the electronics to be really close to the photonics for the energy efficiency to happen. It just, that's the physics. So you got to go 3D. And so when we were poor, well, I'm always poor, but when we were really poor, before we got more funding, we could only run MPWs, right? So what does that mean? Multi-project wafer runs, right? So you submit your designs as part of a lot of other people, and all you get back is your little die. So we submitted designs for the photonics, we submitted designs for the electronics. Electronics is just 28 nanometer TSMC, nothing special, because we're not running at very high speeds. But then we tried to package the damn thing in basically flip chip the electronics on the photonics or the photonics on the electronics. And it's really, really hard because to get the bandwidth density that I want to get, this 5 terabit per millimeter squared, we need to have pretty tight pitch. It's about 25 microns or so. It's not anything, you can get a lot, it's not the technology limit. You can go sub 10 microns these days, maybe even better than that. But in order to do that, you can't do it at the die level like I tried to do here. So we succeeded partially. So this was our first result, and it succeeded, but the yield was not so good. We had some devices working, some not working, So, and the reason is that, when you do die level stuff, you don't have the ability to use the really expensive tools that are designed for 300 millimeter wafers, right? And that's where the magic comes in. So then we got lucky and we got some funding, and we were actually able to have the entire reticle to us. So I tell some of my students went through that whole process of first just doing MPWs and then getting the opportunity to do the full reticle. But some students, they just came in to the group, right? And they're like, oh, we always do the full reticle, right? So and I have to tell them, no, this is like flying first class, okay? It's, you don't get to fly first class, right away. And then, once you do, it's hard to go back, right? So this is like flying first class. You got the entire reticle to yourselves. You can design anything you want. You can tell the fabrication facility to do what you want them to do, and so on. And the other advantage is that what I'm talking about today is the packaging. So this is the name of our full reticle, Cedar. We actually have, since then, we've actually taped out another one that we call Oak. You can see the tree themes. And then from now on, it's going to be really hard to go back to MPW runs. But this is a big enabler, right? Okay, so we did that. And now, using the entire 300 millimeter wafer, we were able to work with a packaging foundry that could do the bonding of the electronics on top of the photonics, can do the bumping and the bonding with extremely much better precision, right, than trying to align. The way we tried to align the 2 die was, for those of you that are interested in some of the details, is we basically waferized the 2 dies. You put the die into kind of like a wafer container, and then you do it's really hard and it's a mess. But this is the real way to do it. And so when we got these results, this first kind of hello world results where we knew that the photonics was connected to the electronics, there was a lot of cheering going on, and it was very exciting. And so this is the chip. This is what we got. This is 5.3 terabit per millimeter squared multi-chip module. So this is you see like a lot of bumps, but basically this is the RX and this is the TX, and it just repeats itself all over the place. And on the lower right picture, you just see the fiber. So we basically have a fiber array that's connected to this prototype, right? So you can take out the data out of the chip, all the wavelengths together in one fiber, and then the next link and the next fiber, and so forth. And then in this particular picture, just the background is that the student that was really leading this effort was away, and we needed to get a picture for DARPA of this chip. And so the younger student came into the lab to take the picture, and we said, put like something near it, like a dime, so that we get a sense of the size. And he put the dime like right on top of the wire bonds, because we still have wire bonds, around this chip. It's a prototype. The senior student almost had a heart attack, but somehow it survived and it worked. So this is a little bit of the inside baseball of what's going on there. So it worked, and it worked really well. We have 100% yield. So this is 80 channels coming out of this chip. In this particular example, they're modulated at 10 gigabit per second, because that's where the most energy efficient point is, operating point. We can also modulate them at 16 gigabit. We can modulate them at 25 gigabit. So we can get higher bandwidths. But this is where the best compromise that we have between the bandwidth density and the energy consumption. And what you see here is the transmitter part. And the transmitter is modulating all 80 transmitters are on, and it's a 1 volt swing on the modulator, and it's 50 femtojoules per bit. 50 femtojoules per bit on the TX side. This is a record. And to prove that, this is also the bit error rates, those of you that are familiar with taking bit error rate curves. So the green is the best, but that's using 1.5 volt swing. But the blue is still completely error-free all the way to the 10 to the minus 12, and is at the 1 volt swing. So that's the lowest energy one. And then the receiver. So the receiver is always problematic. It's always hard to get the receiver to be low energy too. And so it took us a little bit longer, but these are the measurements from the receiver side. So again, 80 receivers with the filters, going in there, and at 10 gigabit per second. And the thing that really made this incredible was that the receiver sensitivity is like almost minus 25 dBms. So if you look at some of the best telecom receivers, they're not even close to this. This is like this is just a very, very good performance for a receiver. But the record performance is on the energy consumption. So the total energy consumption of the receiver here is just under 70 femtojoules per bit. So the TX is 50, the RX is just under 70, so that's about 120. And I told you that I was less than 250 for the entire link. So the other two parts are the laser and the stabilization of the heaters. But this is very, very happy with these results. This is the picture of the prototype, fully packaged, and sort of the board that we used to test it. And then we actually we took two of them and we connected them together over 100 meters, and it's working without any optical amplifiers in the way. It's just MCM to MCM over fiber directly, error-free. But so far, we've only been able to do 8 gigabit per channel. Not as high as we were able to do it when we just test the transmitter and the receiver separately. And it's really because of it's the clock recovery on the receiver that's limiting this measurement. But we're still, really, really happy with it. So it's, come on. Okay. All right, so kind of pulling out a little bit, right? So showed you a lot of technology, optical technology. Maybe some of you went to sleep on that, because this is a computing conference. so what can we do with this, right? I mean, yeah, 5 minutes, okay. What we can do with this is, I think we can potentially change how we think about the interconnect architecture in computing systems, right? So this is from Fabrizio at Intel. He gave me this chart, and he's like, look, the needs for memory and I/O is gonna double. Maybe it's even worse than this, already. So this is, we're all very familiar with this. So here's kind of what I'm thinking we can do with the photonics. So one of the problems, right, is that we can't get all that bandwidth off the socket today, right? So as soon as we get off the socket, we're like, we're back to hundreds of gigabits instead of the terabytes. So what if we, use these photonic I/O chiplets to take all that bandwidth off? So now we can actually have terabytes connecting these sockets together, instead of just, maybe increase that by 2 orders of magnitude. And also, we're maintaining the energy. So, this data movement is happening at a lower energy than those pluggables that we have today, those 800 gigabit pluggables. They're awful. They're like 10 picojoules per bit at least, if not 20. So this is at least a factor of 10 less than the pluggables today, per bit. And so what if we could think about disaggregated architectures? For example, we could put a whole thing of high bandwidth memory that we can connect to with very, very high bandwidths. So this is kind of, and at least the vision that I'm thinking about is, we can use the photonic connectivity to really disaggregate the system in a more deep way, so that when we're running an application, right, let's say we need 10,000 GPUs, we don't have to connect to the socket that has, the GPUs that we want, but also the CPUs and the memory and their brother. We don't need to take everybody for the same ride. We can just connect to the resource that we need. And that's a kind of an energy efficiency, potentially, thing to do. And we can also use the photonic I/O to connect to photonic switches, or even electronic switches. Just have an optical I/O to the electronic switches. Basically reflect, replace the NV type of switch, for example, with, instead of having those 200 gigabit or whatever they have, 400 gigabit, NV links, the photonics will take that bandwidth density much, much higher. And, this is kind of like a more system level ideas that we're thinking, but definitely, need to talk to the actual computer architects today. So, all right, so that's all I have. I just want to, show a picture of the people that actually do all the work, and thank you so much.
Thank you.